Okay, so watch and listen carefully here. Question number one is pretty much like all the other two-part V equals D over T questions we've been doing. Okay, we got a marathon runner who runs fast at the beginning, but then slows down for the last 10.6 kilometers. Okay, if I want to find their average speed, what two things am I going to need? Total distance and total time. All right, so if we're looking at the breakdown of that, right, the first thing is give them a mark if they wrote down their givens. In part one, we knew the speed, 7 meters per second, and we knew the time. All right, I changed it to seconds, right, because they had it in hours, and I need to make the units match. So I multiplied 1.2 hours by 3,600, and I got 4,320. Okay, the other givens were the speed in part two, 6.1 meters per second, and the distance traveled, which I changed to meters because they gave it to me in kilometers, 10,600 meters. All right, they do not have to have made those conversions to get the givens mark. All right, I need total distance and total time. In part one, I don't have the distance, so that's the first calculation I've got to do. All right, so we get a mark for that right here. Okay, D equals V times T. So I take my 4,320 seconds, multiply it by 7 meters per second, and I get 30,240 meters. So 1 mark for that step. They don't have to have got the answer right as long as they showed that they were multiplying V times T. Okay, it's a method mark only. All right, this mark here that's kind of in the middle, right? That's the mark for converting the distance to meters and the time to seconds. So as long as they did that somewhere in the question, you can give them that mark. All right, now that I've got the total or the distance for part one, I got to go over to part two and get the time because that's the thing I was missing from part two. So they get a mark for the manipulation / calculation of time where they manipulated D over V equals T, or they maybe had 10,600 over 6.1, whichever. Okay, when they do that, they get 1,737.705 seconds. Okay, so 1 mark for that step. Now that I've got all the D's and all the T's, now I can do total distance over total time. So if they've got that written down somewhere, okay, or they showed it somehow, give them a mark for that, okay, and then another mark for plugging in the numbers, whichever way they did that. Maybe they showed the numbers they were adding like this, or maybe they just showed the totals like this. Either way, it's the same thing. All right, so we add because distance is scalar, the 30,240 and the 10,600. Of course, we weren't given direction anyway. Okay, 4,320 plus 1,737 for the total time. Okay, so that gives us our totals there. And then for their seventh and final mark, the average speed of the runner is 6.74 meters per second. If they only had like 6.7, that's fine. They did it right then. Okay, questions on number one. 7. Okay. All right. Has anybody seen this absolutely terrible movie? Okay. It's like back in the 80s. It's awful. Yeah, the Cannonball Run. It's this cross-country race across America. Okay. And there's like the redneck team. They have the 4x4 that can go anywhere. And then there's this team of like Arab princes or something like that. The guy who played Klinger in MASH is one of them. And yeah, they have this Lamborghini Countach, the old one from the 80s that looks like a doorstop. Okay, yeah, with the gull wing doors. They had that, and they were racing. There was a bunch of other kind of weird cars and strange people and terrible acting and no plot. But anyway, yeah, so it's a total B movie. So they got to race across. If I want to figure out who wins, what do I need to find out about both of them? Candy? I got to do 2 V equals D over T calculations for time. Fastest time is the winner. All right, so give them a mark if they had the givens down. The car has to go 980 kilometers. The speed's 110 meters per second. The truck's got to go 295 at 32. Okay, give them another mark for doing this calculation here, okay, where they did T equals D over V. Okay, to find the time for the car, so that's 980,000 meters, okay, over 110 meters per second, and that gives them 8,909.1 seconds for their time. Give them a mark for the answer for time. Okay, calculations for the truck. Okay, since you already did this manipulation, I'm not giving you a mark for it. Okay, but if they have the time 9,218.25 seconds, you can give them a mark for that. Okay. And then, if they wrote somewhere that the car wins, that would be their 5th mark. Okay, because the car obviously has the shorter time. Okay? Incidentally, the only really cool thing in this movie, the Mythbusters tried to debunk, but actually found it's possible, and that is that you can skip a car across a river. Okay, because that's one of the scenes in this movie is the Lamborghini is going fast enough that when it hits the water, okay, it goes like a rock and jumps and skips across, not jumps over like the Dukes of Hazzard, okay, like leaps and then skips across this water, okay, and they actually prove that it's possible provided you have a car that's like a Lamborghini where the engine is closer to the middle of the car and the car is balanced, otherwise the car noses in or goes like this and sinks. So it has to skip, just like a rock, right? You can't skip a rock unless you kind of lay it on its side and throw it across the water. Anyway, that's the only really cool part about that movie. All right, so the whole thing is out of 12 marks. So give them a mark out of 12, let them see it. Put it in the box, please. Okay, so if you're taking math, you might be taking this already. I'm going to just briefly go over the old-fashioned building of a graph. Okay, we don't build graphs by hand very much anymore, but it's still kind of valuable to know the format of a graph. And then we'll go over things like slope calculations and stuff like that. Okay, we're not going to spend a lot of time actually building graphs by hand because it's just not something you need to know really how to do. You can build them on the computer, and that's something that we're going to go over later on in the unit as well, how to use Google Sheets, okay, things like that. Basically, any spreadsheet will build a graph for you and how you can get it to spit out all the useful information, okay? All right, things we need to remember about graphing. One of the things we got to remember, okay, is that the vertical axis is the y-axis and the horizontal axis is the x-axis, okay? All right. The manipulated variable always goes on the x-axis, and the responding variable always goes on the vertical axis, because we want to see what happens to the responding variable as we change the manipulated one, right? So we see change in an experimental graph by looking at the vertical part of the graph, okay? We know what we're changing is always going to be the horizontal part of the graph, right? Now, we talked briefly yesterday about how time is very often the manipulated variable, okay? And it's not because we make it run faster or slower, okay, or backwards or forwards, because we can't do that, okay? It's that we manipulate time by determining the length of an experiment. Right? If we're, like a lab we're going to do is we're going to run some motorized carts down the atrium. Okay? We determine how long the experiment runs for. We run it for 40 seconds. Okay? So everything else is dependent on how long we let the experiment go for. How far the carts go is going to depend on how long we let them run for. If we let them run for 20 seconds, they're not going to go as far. If we let them run for a minute, they'll be across the gym. All right, you guys follow me there? So in that way, the time affects the other things. Time can always affect other things. So time is very often the manipulated variable. All right, we always want to label our axes, okay? And those labels should include the units being used for that particular measurement. Okay, and that's often something that people forget. Okay, and the reason I make such a big deal out of having the units on there, okay, is that this says time versus speed for an accelerating vehicle. Okay, if I just have speed on here with no units and my graph looks like this, I might think, well, that line's not very steep. That car's not very fast. Okay, but I might be thinking to myself, well, the units are probably meters per second, so it's not that fast. But what if the units were kilometers per second? Now does that line mean something entirely different? Now it means that this is a jet-powered car, okay? And it's really fast, ridiculous, all right? But that's the importance of units. It really leads to an incorrect impression of what the graph is telling you. If you don't have units, it really eliminates a context for you, okay, in terms of determining what the graph is saying. All right, and then title your graph, okay, and your graph should have a descriptive phrase, okay? Yes, it should also say, you know, what two things are on it, time versus speed, or distance versus time, or position versus time, whatever. It should have that on there, but then give it a context, okay? This is for an accelerating vehicle, not a caterpillar crawling on the road, okay? Because those are obviously, that's a big difference in what we're going to be graphing. Okay, so you always want to have a descriptive phrase that describes the relationship. Now, for scale, okay, scale is the part that people really struggle with. That's why it's nice that we actually do it on computer now, because then the computer will spit the scale out for us. What we mean by scale is, what do we need to make each line worth on the graph? Okay, is it important that every line or every grid on the graph is worth the same amount? Yeah. Okay, because otherwise I can't draw relationships between the two because there's gaps, okay, on one axis. Okay, so every line's got to be worth the same amount, and we need to make sure that we use up as much of the graph as possible. Right? I often have people, when they build a graph by hand, if this is their sheet of graph paper, their graph is like this. It's like, how are you going to do any calculations with only that much graph? Right? Why didn't you pick a scale that went all the way out to here and all the way up to here so that your graph could be this big? It's way easier to work with a graph that's big. Okay? Because then you get more data points. You get more grid intersections where all of your lines are. Okay? It just works out a lot better than when your graph is only this big. Okay? So we always want to take up as much space as possible. All right, now again, it's not something we have to do all that often anymore because the computer will do it for us. Okay, so we want to use a scale that's easy to use. Like, I don't want to make every line worth 1.37892 because that's ridiculous. Then I have to, okay, 1.39872, 2.7, blah, it's ridiculous, right? You wouldn't want to pick a number. It's not convenient, okay? I could just as easily go and make every line worth 1.5. Way easier to count by 1.5 than 1.3 whatever, okay? So I go 1.5, 3, okay, 4.5, 6, and so on. And, right. I did that right. Okay, yeah. So that's how it would work, okay? You pick a scale that's easy to count by, but that's close, okay, and that'll fill up as much of the page as possible, okay? And then again, remember that each square needs to represent the same amount. Okay, when you're picking that scale, the way you figure it out is you take the biggest number that you have to fit on the graph, okay? So let's say that we have this, that we have to fit 700 on the graph, and we only have 30 lines on the graph. Okay, so if I want to figure out what I got to make each line worth, I go 700 divided by 30. Okay, that tells me what each line on my axis is going to be worth. Now, when it spits that out, it spits out 23.33333. Do I want to count by 23.333? What can I use instead? 25. Okay, I could use 23, but 25 is close and easier to count by. Right? So that's what they mean by choose a scale that's fitting but convenient. All right? You wouldn't want to pick 50, okay? Because if you pick 50, then you're only going to use up less than half of the graph. Why couldn't I pick 20? 20 is also close to 23 and easy to count by. Yeah, I won't make it. Okay, if I pick a number smaller than that number, I'll run out of lines before I run out of numbers. Okay, so you always have to round up when you're picking a scale. So it's 23.33. I got to pick 24 or 25, okay, something that's convenient and bigger. Otherwise, I won't fit it all on there. Okay, so then I would make up a scale that looks like this: 25, 50, 75, 125. And this person obviously has way neater handwriting than me. Okay, if it were me with my handwriting, I would make the scale look like this. Are these two scales the same? Yep, every line is still worth 25. I just didn't write every single number. Okay, people still understand that that line is 25, 50, 75. I just don't have to write them all on there. It makes your axis not as crowded, especially if you have terrible handwriting like me. Okay. All right. Once you have your axes done and labeled and you got a scale on each of them, then you can start plotting your points. Okay. How do we plot points? Okay. We just look at their values. If I have got a graph that looks like this, let's say it's 1, 2, 3, 4. Okay, and my first point is, let's say this is time in seconds, and this, whoa. Okay, well, that's not the graph I was using. There's the graph I was using. Okay, let's say that my first point is 6 meters and 2 seconds. All right, so I go over to 2 seconds, and then I go up to 6 meters, plot my point. Okay, so you use your X, go up for your Y, plot your points. Okay, pretty straightforward on that. How accurate can you be when you do that? The answer is it actually depends. It depends on what kind of numbers you're getting. If I get 2 and 6, that's an intersection of grid lines on my graph. I could just put it right where the grid lines cross. What if it's 6.15 and 2.37? How accurate am I going to be now? Probably not as good, right? Because I'm aiming in the middle of a square. Okay, so if I had that instead, it would be, right? Those are my graphing lines there. Okay, I'm aiming for something in this box, and I'm like, okay, 6.1 would be about here, and 2.3 would be about there. Okay, maybe there. Right? Don't know for sure. Now there's some error in those plots. Okay, that's again why it's nice to have the computer do it, because the computer will set it up with pixels and they'll put it in exactly the right place. Okay. So like I say, building graphs by hand has really become kind of a dead skill, right, in terms of actually doing it, but understanding how to do it is still important. You need to know that when a computer spits out a graph, what did it do in order to spit it out, okay? All right, so I wouldn't worry too much about number 8, okay? When you had to graph by hand, you had to do either error bars or circles around that indicated how much error there was in the placement of your point. So every point on your graph looked like this. Okay, because there could be error that much horizontally and error that much vertically, and you had to indicate all of that. Some people drew a circle around it. I'm not going to have to do that. Okay. 0, 0 is called the origin. Just in case you hear me use that term, you know what it means. Okay. The origin is this point here where the y value is 0 and the x value is 0. It's where the graph originates. Okay. All right. Questions so far? All right. Okay, so other terms here, okay, grid lines are obviously the lines that are on the graph. Okay, grid line intersection is where they cross. Okay, any place where the grid lines are crossing. Okay, so these spots here, okay, would be grid intersections. X-axis is the horizontal axis, Y is the vertical axis. Okay, remember which variable goes on each. A best fit line is the most important tool on your graph. Okay, because the best fit line tells us the relationship that exists between the two variables. Okay, sometimes it's not a line, sometimes it's a curve. Right, that tells us something important as well. All right, so if I've got a bunch of points, I want to draw a best fit line. Right, so let's just say I've got kind of a rough graph that looks like that. My points look like that. Okay, my best fit line needs to follow the trend of my points. Okay, in math, they'll sometimes tell you should have same number of points above and below. And while that's an okay guideline, I don't like it as a hard and fast rule. Okay, because sometimes that doesn't actually follow the trend of the points. What do my points in general do here? They generally go, they're going up. Okay, so my best fit line should go up, not straight up, but diagonally upwards. Okay, where should it start? Well, I mean, it could start at the origin, but I think actually I could make a better adjustment of these or a better average of these points if I didn't start at the origin. And you don't have to start at the origin. The most important rule is that you follow the trend of the points. So on a graph like this, I could draw a best fit line that looks like that. And that follows the trend of my points pretty well. Okay? I think if I had it at the origin, it might be a little bit steep. Okay? Here's why I tell you it doesn't need to start at the origin. I want to draw a best fit line of those points. There is absolutely no way I can draw a best fit line from the origin that follows the trend of those points. Agreed? Okay, because those go down, right? No line I could draw from the origin would approximate what's going on there. Okay, so you always start wherever you need to follow the trend of your points. Okay, now again, spreadsheet programs like Google Sheets and Excel, and I don't know what the Mac version is, but okay, they'll all do this for you. They'll draw a best fit line on for you, okay, and they'll draw it wherever it needs to go. Okay, now once we have a best fit line, what do we want to find out about it? Rise over run. We want to find out its slope. Now, you can use rise over run, or you can also use the graphing equation, okay? Y equals mx plus b. How many people have gone over that in math already? No? Okay. So we're going to do a little bit of graphing anatomy here, because rise over run actually comes from this formula. Okay? So let's just... Okay, let's look at this graph here. We'll use this as kind of our example. All right, I've got this graph. It's distance traveled in time in hours, distance traveled in kilometers. Okay, I want to find the slope of this line, and I want to use y equals mx plus b. Now, we need to know what each thing stands for in here. Okay, y stands for the y value, okay, the vertical value of a point that is on your best fit line. And that's the key. I can't find the slope of a line by using points that aren't on the line. Okay, that's the most common mistake I see people make. Okay, they'll have, let's say that the points used to plot this line look like this. Okay, oftentimes when you draw a best fit line, none of your points actually end up on it. All right, to follow the trend of the points, sometimes that happens. Well, I can't use this point here to calculate the slope of that line because it's not on that line. You guys follow me there? It can't tell me anything about the line, right? So I can't use it. So I need to use, let's say, this point. Okay, it's on the line. It's an intersection of grid lines. So I know the exact values of y and x. Okay, so that's where we're going to get y and x from. From this point, y is, this is 3,000, so this would be 4,500. Okay? Everyone follow me there? This is 4,000, so that's going to be 4,500. So the y value for that point is 4,500. What's the x value for that point? 30. Okay? Everyone follow me there? So that's what y and x are. They're the x and y values for a point that's on your line. Could be any point on your line. Okay? Right? If I was using this one, I would use the same for that. And I'll show you why that'll work in a minute. Okay, so I've got y and x. What's b? Not quite. B is what we call the y-intercept. Okay, the y-intercept is where your best fit line crosses the y-axis, where it intercepts y. Okay, so our y-intercept is right here. Okay, that's B. Okay, that point right there is B. And I'm going to have to estimate a little bit. It's not quite 500, it's a little more. I'm going to say it's about 600. Okay, everyone all right with that? Don't like having to estimate, but we don't have any other way on this graph. So I'm going to say that B is 600. We've already figured out that Y is 4,500 and X is 30. All right, what does M stand for then? Only thing that's left, the thing we wanted to find. Starts with S. Slope. Yeah, we want to find the slope of the line. Okay, the slope of the line tells us the mathematical relationship between whatever's on the y and whatever's on the x. Okay, all right. So if I want to solve for m, for the slope, I've got to do some algebra, right? Okay, quick review here. The 2.5 rules of algebra are: you want to move something, do the opposite, then do the same thing to both sides. And what was the half rule? Okay, yeah, I always say it as move what's not attached first. Okay, if I'm trying to solve for m, what's not attached to m? B. B is not attached to m. X is attached. They're being multiplied by each other, but B is over here, it's separate. Okay, so B is not attached. How do I move B over to the other side? Subtract it. Okay, so I'm now going to have y minus b equals m times x. Now what do I do with x? Divide by it. Okay, now I've got slope by itself, m. Now, slope, you've been told, is the rise, how much the graph goes up, divided by the run, how much the graph goes over. All right, everyone follow me there? Okay, if I go y, this number up here, minus b, did I just calculate how high it goes? Okay, so I just calculated the rise. Okay, and what's x at this point? 0. X is always 0 at the y-intercept because where the y-axis is, x is 0. Okay, so this x is this number over here, 30. Did I just go 30 minus 0 and figure out what's on the bottom? Okay, so x is basically the whole run of the graph. How long is the graph? So this is rise divided by run. Okay, in math, they might have showed it to you like this. Okay, did they show it to you like that, area? Rise over run, y2 minus y1 over x2 minus... No, you're not in math? Who's in math right now? Okay, so this is all new to you. Good. I'm not going to ruin you. I think this ruins people. I don't like it. Okay? Okay. If you never learn that, you'll be way better at graphing because you use this formula. Okay? So when you do this, you're finding how much the graph goes up, y minus b, divided by how much it goes over. That's slope. Basically, how steep is the line. Right? Now, for this graph, we can plug in our numbers now. Y, we said, was 4,500. And b was, I think we said 600, right? Okay, and x was 30. All right, these were meters. And this was, or sorry, these were kilometers, sorry. Kilometers and this was hours. Yeah, you're right. Okay. Did I just figure out the displacement on the top and the time on the bottom? Yep, because I started at 600 and I went to 4,500, okay? And it took 30 hours to do it. I just went displacement divided by time. That's the relationship between distance and time. If I divide distance and time, I get speed. If I divide displacement and time, I get velocity, okay? So this graph can tell me the velocity of an object even if I don't necessarily have like the total. Okay, if I don't have the total displacement and the total time, I could use some of the other points to figure it out, okay, and approximate it from that graph. All right, so I would find the slope here, and it would be in kilometers per hour. It's really important when you do a slope calculation to look at what your units are going to be. Okay, so we're going to have 3,900 divided by 30, okay, 4,500 minus 600, okay, over 30, so... Right, so our average speed is 130 kilometers per hour. Everybody okay with that? Okay. All right, the reason I like using this formula versus rise over run is I only have to find one point on my line. If I use rise over run, I got to find two. Okay? I only have to find one point on my line for this because I know where B is always at. Okay, B is always where the y-axis is. All right. Let's just do a couple here so that we kind of get the hang of how this, well, we might get one done today. Okay, get the hang of how this works. Okay, I'm going to give you this sheet here and a sheet of graph paper. We'll do this one by hand just to do the exercise here. So we're going to graph these two variables, diameter and circumference. So I'm going to make diameter my manipulated variable because it kind of makes more sense that if I increase the diameter, the circumference would also get bigger. Agreed? Okay, so I'm going to make diameter my manipulated variable. It's going to go on which axis? It's going to go on the x-axis. Okay, there's 30 lines on the x-axis. Your graph might have a little bit more, but we'll just say it's the same size as mine here. Okay, there's 30 lines on the x-axis, and there's 37 on the y-axis. So I got to figure out what each line is going to be worth. The biggest number I've got to fit on the x-axis is 7.4, and I've got 30 lines to do it. So what do? Other way. 7.4 divided by 30. Is it okay that I get a decimal? Yeah. It's okay, just means every line is worth a decimal, okay? But it's going to mean that my graph will be nice and big and I'll be able to use it effectively. All right, so I'm going to go 7.4 divided by 30. 0.246 repeating. Can I round that to 0.25 and have a nice easy number to count by that'll fit? Perfect. Okay, that's what I'm going to do. All right, so this is 0, and I'm going to make each line worth 0.25. But to save time and to avoid my messy handwriting, I'm only going to write every fourth line. One, 2, 3, 4, 5, 6, 7, 7.5. All right, perfect. It fits on there because the biggest number I had was 7.4. Okay, so it's going to fit. All right, people will still understand looking at my graph that every line is actually worth a quarter. Okay, but I'm not drawing them all on there. Okay, same thing with the y-axis. Okay, the biggest number I've got to fit on there is 23.1, and I've got 37 lines to fit it on. All right, so sorry, it's 23.1. Okay, divided by, I've got 37 lines. All right, 0.624. Yeah, it's not great. Let's use 0.7. We can count by sevens, right? Count by sevens isn't too hard. All right, I'm going to make it 0.7. All right, so every line's worth 0.7. That makes every second line worth 1.4. 1.4 is 4.2. 4.9, 5.6. 6.3, 7, 8.4, 9.8. No, that's not right. What am I doing here? Okay, 1.08.